Hello, I'm Barry Vann. Welcome to the Vantage Point. Have you ever heard the Johnny Cash song Ring of Fire? It was written by his wife June Carter Cash and Merle Kilgore. Doesn't the title sound foreboding? In truth, the song is about falling in love. It's been claimed by some that June saw love as like a burning ring of fire underlined in one of her uncle's poetry books. That might be true, but if she really did fall into the burning ring of fire, she wouldn't have survived more than a second, because it's a lot hotter than most fires that mere mortals can make. In fact, in everyday life, we often use rocks to keep our feeble fires from spreading throughout our homes and forests. In the ring of fire, it's so hot that it melts rocks. Today on the Vantage Point, we're going to take a look at the major features of the ring of fire. Before we get going though, I want to thank David Wyatt for his suggestion of this topic. Thanks, David. I hope you'll join me. Well, the real ring of fire is about earthquakes, volcanoes, and trenches, not love. It forms a horseshoe shape near the continents that surround the Pacific Ocean, including North and South America. This explains why California has a history of earthquakes. In length, it's about 25,000 miles, which is about the circumference of the Earth at the equator. There's not a good scientific explanation for that similarity in distances, so it's purely coincidental. The average width of the Ring of Fire is about 300 miles. In reality, volcanic eruptions in the tropics, that's 23.5 degrees north to south, as we'll see today, are much more likely to impact the entire planet than similar eruptions in mid-latitudes like Mount St. Helens. Indonesia, for instance, has witnessed two of the most powerful and deadliest eruptions in recent history. In 1815, Tambora erupted, and the ejection of pyroclastic material killed approximately 100,000 people. Mount Tambora's impact wasn't limited to Indonesia. Particulate matter from the eruption was suspended in the atmosphere, where winds distributed the material around the world. Nature's suspended pollution caused a reduction in solar rays passing through the atmosphere, with less solar energy reaching land and especially the oceans. Tropical waters of the planet cooled. Consequently, ocean currents carried less energy from the Earth's zone of energy surplus into its zones of deficit. Cooler water impacted weather and climate around the globe over the next 12 to 18 months. Historians and geographers call 1816 the year without a summer. I did a video on that topic a few weeks or months ago. A second Indonesian event happened when Krakatoa erupted in 1883. It's been estimated that 36,000 people were killed by that event. One might wonder why Earth has a ring of fire in the first place. The Earth's land surface, as most first-year college students learn, only covers about 30% of the planet. So, most of the crust lies under the oceans of the world. There's a significant difference in the thickness of younger oceanic crust and older continental crust. The crust is thinner under the oceans than it is under the continents. The crust ranges from about 5 kilometers or 3.1 miles under the oceans to 70 kilometers or about 43.5 miles under the thickest portion of a continent. The crust is thickest under mountain ranges like the Alps, the Himalayas, the Rockies, and the good old Appalachian Range. If we could travel to the center of the Earth, we would find that our planet gets progressively hotter as we approach the core. We would also find that the Earth gets denser as we descend toward the center. Heat from the Earth's interior is transferred through conduction and convection to cooler, less dense areas of the Earth's mantle and crust. Under heat-generated pressure, magma, or molten rock, is pushed upward to the weakest or thinnest parts of the Earth's crust. In the Atlantic and Pacific, lava, which is what magma is called when it's exposed to an ocean or the atmosphere, is excreted through those weak places. They just bust open and come up in the seafloor. They form undersea ridges and mountains. We call this process seafloor spreading. As undersea plates move in opposite directions from mid-oceanic ridges, they'll collide with other plates that are moving toward them. The North American continental plate actually originates at the Mid-Atlantic Oceanic Ridge. So when the western Atlantic seafloor spreads or moves westward, so does the landmass where we live. But don't be too alarmed, because we're only moving a few centimeters or inches per year. Meanwhile, in the Pacific Ocean, the seafloor is spreading eastward and westward from its mid-Atlantic or mid-oceanic ridge. The plate on which the eastern Pacific actually sits collides, albeit at a really slow speed, with the North American and South American plates. Being denser than the continental plates, the seafloor actually bends downward and is forced under the Americas. Friction and the Earth's interior heat melt the submerging oceanic rock or crust. The same process occurs on the eastern side of the Pacific. We call these impact areas subduction zones. Under friction, the continental crust develops fissures or faults. It's through these fissures that new magma, which was formed by the melting of oceanic crust and rocks, is pushed upward to the surface of the coastal areas on the continent, where they form mountain ranges. The coastal ranges of California and the Andes in South America were formed by this process. By looking at a map of the Earth, we can see that volcanic mountains made of fire-borne or igneous rocks parallel subduction zones. If we look at the ocean basins, we can also see mid-oceanic ridges. What's not obvious to those who spend little time thinking about what lies on the bottom of the seafloor or the landforms under the oceans is that the shape or morphology of the seafloor is also affected by or impacted by the collision of oceanic and continental plates. The map of the seafloor shows that trenches also form in parallel fashion to the subduction zones. The deepest parts of the world's oceans are found in these places, trenches, canyons, whatever you want to call them. In the Western Pacific, for example, the Mariana Trench forms a crescent-shaped canyon that's 1,580 or 2,500 kilometers long. Get this, in its deepest place, it's 10,984 meters, but thinking of it in feet and miles, the Mariana Trench is 36,000 feet deep. That's about 6.83 miles below sea level. If we're talking about the distance above the Earth's surface, a concept that's called elevation, we would be at the highest altitudes that commercial jets fly. In fact, we could stack Denver, Colorado, the mile-high city, on top of Mount Everest, and we would still be over 1,000 feet lower in elevation. Without a supply of O2 and pressurized suits, we wouldn't stand a chance. The forces of nature are powerful, and that's an understatement. They're all around us. The vast majority of the Earth's volcanic eruptions and earthquakes happen along the 300-mile-wide expanse of land and seafloors that straddle subduction zones. These locations are among the most strikingly beautiful places on Earth, but like a low-lying tropical island situated in the Bay of Bengal, Hurricane Alley, there's great potential for massive destruction. Stratovolcanoes that erupt in the tropics are significant for two reasons. First, they obviously kill plants, animals, and people, as well as destroy property. Second, as was the case in Tambora's eruption in 1815, they can impact weather on a global scale. I hope you got something out of today's show. If you did, I invite you to hit the subscribe icon, and while you're there, tap the like button. You know, I read and respond to appropriate comments, so if you'd like to have a dialogue with me, please post them below. I'll write you back. Until next time, God bless you and yours. Bye-bye.